Yeah, so that's today's topic, but as promised, I want to tell you a bit about the proof of this homotopy invariance of the algebroid cohomology, because I like it so much. So let's get back for a few minutes to yesterday. So we defined the algebroids. Then we defined the algebroid homotopy of the algebroid. So if you have two maps, two Lie algebroid morphisms from A to B, then they are said to be LA homotopic if you have a Lie algebroid morphism from the product Lie algebroid Ti times A. I is an interval containing 0, 1 over I times M, 2B times N, such that the compositions of phi with the two inclusions of A at time 0 and at time 1 are then your Lie algebroid morphisms phi 0 and phi 1. And then we had also LA homotopy equivalence of Lie algebroids, but we don't need it now. And I wanted to tell you a bit about the proof of this homotopy invariance of twisted Lie algebroid cohomology, because as I said, I think it's a good argument for the notion of Lie algebroids, because even in the case where A is Tm, to our knowledge, it was not known yet that the twisted, the RAM cohomology, so the RAM cohomology with values in representations of Tm was homotopy invariant. And I just want to show you in the proof where you have to leave the smooth world, even if A and B are just tangents of smooth manifolds. So the sketch of proof is as follows. So first assume that you have a Lie algebroid and a vector bundle F over M, which has a representation of A. Then if you choose a section and you consider the flow, so let's call it psi, the flow of the anchor of A. So omega is the flow domain. I usually write it like this. Open subset of R times M containing 0 times M. That's the flow of this vector field. Then if you consider nabla A, so nabla A is, as Janus said yesterday, is rightly a derivation of F. So a linear derivation of F. So when I write this, I mean the corresponding vector field on F. So we get a linear vector field on F. Linear vector field. A linear vector field has a flow by vector bundle isomorphisms, sorry. And you also have, in the same manner, the bracket with A. The bracket with A is a derivation of A now, of the vector bundle A, but by Lie algebroid, infinitesimal Lie algebroid automorphisms, Lie algebroid derivations. So its flow will be a flow by Lie algebroid automorphisms. So let's write it. So they have flows yeah, so I should change this letter, but okay, in the paper it's this letter. So their flows are defined on the fibers over the flow of the anchor of A, rho A. So So that goes to F. And similarly, the flow of psi, the flow of this one. Same set, just that here you have A and here you have QA, lambda A, etc. So you have flows that are such that for each T in R, this flow at time T is defined on the fibers of F over the, how is it called, the manifold, the open submanifold of M, where the flow at time T of rho A is defined. So that goes to M minus T, that's T. Then you have QF minus 1 M minus T. So that's iso or vector bundles. And similarly, the flow of phi of the second vector field at time T is defined on the fibers of A over wherever xi T is defined, and that's a flow by the algebroid isos. I mean, that's standard, but you really need these considerations. And then, because for each time T, you have those isos or vector bundles, and specifically here, iso of the algebroids, you can take pullbacks of sections, and then you have then that for all T in R, wherever those sections are defined, then if you take psi T star of B, so for all B in gamma A, for all E in gamma E, the representation nabla along the pullback of a section B under the flow at time T applied to the pullback at time T, so I cannot make those stars, of E is the same as the pullback at time T of nabla B. Sounds very plausible, right? But you really have to prove it and to see it. That's because this is because the nabla defines a Lie algebroid structure on A plus F over M, with anchor just sending AE to a row of A. And this Lie algebroid structure is a semi-direct product of A with its representation, right? So A1, E1 with A2, E2. The algebroid bracket defined by nabla is in the first argument A1, A2, and then you have an extension by the representation, which is really just what you would do with for a Lie algebra with a representation. But if you look at this Lie algebroid, then with the same section A as before, you're going to have this derivation of the Lie algebroid. So this linear vector field on this Lie algebroid, and this statement here that I should call big star is just the fact that that's its flow. So the flow of this one, which now I call I. Same, so it's defined again over the flow of row A. So its flow at time t is defined on the fibers of A plus F over wherever the flow at time t of row A is defined, and then this flow does, because it's a flow by Lie algebroid automorphisms, it does specifically this on a section B0 and a section 0E. So it's just a Lie algebroid automorphism. So why do I say this in detail? Because this is really the advertisement for the language of Lie algebroids. If your A was just TM and you would be looking here at twisted the RAM cohomology, you would still need to look at this Lie algebroids defined by semi-direct products of representations of TM of TM with its representations, right? So and that's the key. Once you have this, I already need to clean the board. You're going to use, first of all, so this is the preparation in a sense. Now we go to our situation where the Lie algebroid is Ti times A, and we have Ti times A representation on, sorry, what am I saying? We have the B representation on E, which we pull back to a Ti times A representation on phi pullback E. Yeah.
Assume that your homotopy is smooth.
Yes. Yeah, I mean, you can make sense of homotopy equivalence by allowing several homotopies between the algebroids, but that is not really interesting to us at first, but you can do it.
Every C0 homotopy between finite dimension C infinity object is C0 homotopic to a C infinity homotopy.
Right. So now step 2, if you have enough. So if you have a, let's discuss this later. So if you have a Ti times A representation, nabla on a vector bundle F, first of all, which is on I times M, then you're going to consider X to be, well, or little a, but let's call it X, to be the section partial T0 of this Lie algebroid. Its anchor is partial T. You see, so sorry, partial T0 in Ti times Tm. And so its flow is super easy, right? Defined on the space of, so what do we have? Lambda Sm in R times I times M, such that lambda plus S is in I, and that goes to I times M, and it just sends lambda S and M to lambda plus Sm, right? I mean, that's easy. So the flow of X so bracket with X, as a linear vector field on Ti times A lives over there. Let's call it again psi. So the flow of this vector field is now going to just preserve the sections of A. So psi T star of pair 0A is 0A for all T in R. And the flow, again, written like this, of nabla X hat, which is a linear vector field on F, right? F is a vector bundle over F times I. It's going to identify your slices of F, right, at different times. So it's going to do psi T restricted to the pullback at time S of F, so the F slice at time S. And it's going to send it to I S plus T pullback of F. For all T wherever this is defined, right? There. So you're going to get, in this way, your gauge equivalences. Your gauge equivalences, which we're going to call theta ST for all ST in I. It's going to be psi minus S restricted to IS pullback F, IS pullback F to IT pullback F, and then a use of star over there. This is a computation. Will give you that. Sorry, let's write it like this. You get those maps, and by star, these are gauge equivalences between now the pullback of the connection at time S on this vector bundle and the pullback of the connection at time T on this vector bundle. So IS pullback nabla and IT pullback nabla. So that's really the key, the crucial step where this star over there is used. So that and that's how you basically you trivialize your F. I mean you have your F over I times M, and you detangle it to well, I times a vector bundle at a special time. But you can do it for each time, and for each time, let's write it here. You get along the way an isomorphism of F with I times IT pullback F over the identity on I times M. And so it's an iso. And then you get gauge equivalent a whole family of gauge equivalent connections on this by just taking the Ti times A connection on F via this isomorphism to a Ti times A connection here, which you call nabla T. So, but basically, this is all a bit the first step in the similar result. Well, the non-twisted, the RAM version of this in Bolton 2, where you first show that vector bundle over I times M is I times the vector bundle at any time, right? Just that here you need to take all the connections along. You also need to take your representation of f, of Ti times A on f, to be a representation of this space, on this space for each time. So for each time you get a representation, but they are all gauge equivalent by construction. So you get a huge diagram, as I showed yesterday, where, so first of all, you have your Ti times A representation of f that gives you this cohomology. Then you have the restrictions at special times, time t, time s. Then the gauge equivalence that we have constructed, that's really where this, this star over there enters the picture. Oops. And then you also have the gauge equivalences giving isomorphisms of this cohomology with the cohomologies on, well, I times wherever you restrict your f, each time you restrict your f. And then you use this result that I mentioned yesterday, that taking the time factor doesn't really change the cohomology. And you also have some, I find it a bit obscure, but it works, step saying that looking at this pullback PRA pullback IT of nabla T is the same as this. Well, maybe it's intuitive. Anyway, you get a huge diagram. Everything commutes. That's the work. You need to show that everything commutes. And then you get that, well, you get this gauge equivalence of those two restrictions. And then if you want to, I know this is very small. I'm really sorry, but otherwise it didn't enter the picture. You can check our paper if you want the diagram in big. Then if you want the result with Rosa about homotopy equivalence, you're going to apply this whole diagram to the situation now where you have, so you have your Lie algebroid morphism, your homotopy, and you have nabla AB representation on some, E over N, and you apply the diagram before to F equals the pullback, pullback like this of E, and the Ti times A representation phi pullback of nabla on it. So you get the bottom part of the diagram, and then you extend it by those two triangles on top, which are just saying that which are just how your maps are defined. So you have the commutative diagrams with the cohomology given by the representation of B on E that pulls back to the Ti times A cohomology with values in phi pullback E. That's the map phi star that we had yesterday. And then for each T, you have, for each T, you have this phi T star to H, phi T star nabla A on phi T E, which is defined by this commutative diagram, basically. Right? So by definition, you have phi composed with IT is phi T, this composition of the algebroid morphisms. So you get this big diagram, and you get, because everything commutes, that the two maps at the left and right are the same up to the homotopy equivalent, the gauge equivalence that we have constructed, right? So, yeah, short sketch of the proof, just to show you that, well, yes, the language of Lie algebroids, well, and linear derivations and linear flows and so on, is useful for this kind of problem, even for showing that the Ram cohomology is an homotopy invariant. Right. So, right. Oh, and I forgot. We also have some other standard results which are generalized to the context of the algebroid, but maybe ask me later. That's all in it's all in our paper, and it will all be in Rosa's thesis as well. So we have a generalized Poincaré lemma, we have a Meyer-Vittoris formula, and we have a Cunet isomorphism for twisted the algebroid cohomology. But now let's get to today's topic. Right. So this background on the algebroid cohomology was because on Thursday I want to tell you a bit about obstructions to the notion of ideal in a Lie algebroid. And those obstructions will be in terms of, well, some twisted Lie algebroid cohomology, and also in terms of Pontryagin characters defined by representations up to homotopy, which we will also define on Thursday. So we leave a bit the cohomology for now, and we are going to look at ideals in the Lie algebroids, but from a very geometric point of view again. So yeah, we'll start by the definition, then we'll motivate it by the process of reducing Lie algebroids, but you can motivate it also differently. And then there will not be time, so on Thursday we'll talk about the Atiyah obstruction, two ideas in the algebroids, and then also the Pontryagin obstruction. Just clean the board. I can let you meditate the next slide. So recall, and that's how I really want to structure these lectures. Recall that we have two corner cases of the algebroids, namely Lie algebras and tangent bundles. In the context of tangent bundles, you will not talk about ideals in tangent bundles. I mean, that's not really something standard. But in the context of Lie algebras, so in that corner case, we have a notion of ideal, which is really important for the classification of Lie algebras, for the representation theory, and so on. So an ideal in a Lie algebra is a vector subspace that brackets the whole Lie algebra into itself. And then there are two ways to reformulate this, actually three ways. I've just decided this morning. So the first way is that an ideal is reduction data for a Lie algebra. If you take just the quotient vector space of G by its ideal, then you have an induced Lie algebra structure on there, such that the projection is an epimorphism of Lie algebras. And the second reformulation of this is that I is a subrepresentation of the adjoint representation of G. And maybe the third, maybe that will be helpful for some of you, is that I defines G times I in G times E. So, sorry, G times G. G times G, you take this semi-direct product of G with its adjoint, little adjoint, so let's write it like this. This is the same as TG. Well, as a vector space, G times G is the same as a TG. So when you look at G times I, you can see it as a vector subbundle of Tg over G, which is involutive because obviously it's involutive, right? So involutive. But you can also, what is G times I? It's actually a Lie subalgebra of G times G. You can reformulate the fact that I is an ideal by saying that G times I is a Lie subalgebra of the semi-direct product, which means that it's actually Lie subalgebra of the tangent Lie algebra structure defined by G. Right? You have a Lie algebra structure defined by G, and you can take its tangent structure, and then G times I is a subalgebra of this structure. So G times I is an involutive subbundle, so subalgebroid over this side, and a subalgebra, so a subalgebroid over this side. So it's a double it's a sub-double Lie algebroid of G times G, which is a double Lie algebroid. We heard the word double yesterday already, right? So it's a double subalgebroid with core I. Whatever the core is, ask me later. But I defines, in this sense, a foliation on G, which is by subalgebras infinitesimally, right? So that's a third useful picture that we will use. Now, let's be naive at first. I always start like this. Let's make the same, or let's try the same definition in a Lie algebroid A. You take a subbundle I in A, such that its set of sections is an ideal in a Lie algebra gamma A.
In this case.
Yes, you're stealing my point. Exactly. You're ahead of the talk. That's exactly the point. The anchor is 0, so that's a super restrictive notion. So I'm going to write that here. The thing is that, because I need this notion as well, if you have a subalgebroid of A, of a Lie algebroid, then you always have the Bott representation of J on A mod J. So it's the flat connection simply defined by the bracket. Sorry, I call it nabla J, that's important. So nabla J, J of the class of A is class of J. So you can check that this is well defined because J is involutive, well, close under the Lie algebroid bracket, and the flatness is Jacobi again, right? So this is the Bott representation of J on A mod J. If J is even an ideal, this representation is 0 because that's always in I, so the class vanishes. But I didn't really say that, but you can maybe think about it for a minute. If you have a representation on a Lie algebroid, of a Lie algebroid on a vector bundle, which is 0, then by the Leibniz rule, the anchor of the Lie algebroid must be 0, right? You can also deduce it right away from there. If you have I with F times A, I is a section of I, F is a function on M, and A is a section of A, then when you write Leibniz, you have this plus F times IA. So this is okay. This is a section of I. This is a section of I. But this is, in general, is not going to be a section of I. If, do I have it on the slide? No. So if A is non-zero, then this is just not working, right? So you need...
Yeah, algebroid, yeah?
Yeah, no, it's transitive.
This kernel is the...
The kernel, yeah. Well, the kernel, but yeah. So you have a... If you have an idea, E, I, and A naive ideal implies immediately that rho restricted to I is 0 or I is A. Right? So yeah, for instance, the kernel of the Atiyah, Lie algebroid, it's the kernel of the anchor, so it's represented on the rest. Right. So then, at this point, you realize that well, either this is the only notion, and then the algebroids become suddenly really not something you want to study. Or maybe there's something else, and there must be something else, because if you look at the other corner case, you have a smooth map from, let's call it big F, because small f is always overvalued. So if you have a smooth map from M to N, that is, yes, let's say a smooth surjective subversion, or let's say a subversion, like the French school. Well, smooth subversion with connected fibers. And then, if you look at, well, if you think about it hard enough, then you're going to see that Tn can be identified with Tm mod Tfm. Tfm is the kernel of Tf. So that's not it, right? Because that's the vector bundle over n, that's the vector bundle over m. But then if you mod this out by parallel transport along the bot connection and defined by this involutive subbundle of Tf, then if everything works well, if this connection has no holonomy, then Tn is going to be this quotient. So you quotient the kernel of Tf, and then you identify your fibers using the parallel transport given by the bot connection. And that's, and that's really a Lie algebroid reduction, because let's write it for sections. So if you have Y, a section of Tm mod Tfm, which is bot flat, so nabla bot flat, so flat section, it's the same as saying that X, or let's write it like this, Yx is a section of gamma Tfm for all X in gamma Tfm, right? If you look at the definition, you replace A by Tm, you replace J by the kernel of Tf, which is a sub-algebroid, then the bot connection is just a Lie bracketer vector field, and if the class of Y is flat, well, it means that Y brackets all sections of Tfm in Tfm. So Y is a vector field that projects to the quotient, right? Y, let's write it like this, projects to a vector field on N. That's basically the idea for understanding this quotient. If you have a smooth submersion with connected fibers, then N is actually the space of leaves of Tfm in M, and its tangent, the algebroid, is this quotient first by the kernel, then by parallel transport, right? And that's what we want to copy to define the ideals in the algebroids, right? So we want to take the point of view that in the world of smooth manifolds, so in the corner case of smooth manifolds, this is reduction data, so it should be an ideal, right? So let's copy this over here.
Foliation with transitive automorphism.
Let's discuss it later. It's just a foliation. Whenever you have a foliation, you can make a quotient like this. If the leaf space is smooth and the bot connection has no holonomy, you will get the tangent of the leaf space by doing this. So it cannot be something very special. So now we consider a fibration of the algebroids. So first of all, let's say are vector bundles. We're going to add the algebroids later, but let's still call them A. So you have A to, let's say, B. You have phi, and phi is over d to phi. So what does fibration mean? I defined the notion of morphism of Lie algebroids in a very abstract manner, but let's walk through it. So, well, first of all, it's of vector bundles, so it's okay for now. So fibration of vector bundles means phi is a smooth submergence again. And let's say that it has connected fibers so that n is again a leaf space of f of m by t phi m. And phi is surjective, fiber-wise surjective. Then when you have this, what kind of data do you have? I mean, then B over N is some kind of reduction of A over M because, well, it's an image of a, well, epimorphism or vector bundles. So you're going to have the kernel of phi in A, that's a vector subbundle. So let's make it abstract over here. So as data, we have a vector subbundle, J in A.
But what is wrong when the fibers are not connected?
Oh, it's because I want N to be the leaf space of the foliation phi m. And if one of the fibers of, well, yeah, if one of the fibers of phi is not connected, then it will consist in several leaves of this foliation. But I really want the fibers to be leaves. Right? I mean, it's just to organize the definition. Right, so the first thing is we have this kernel of phi, which is important because you could quotient A by its kernel first, and then you would still have an epimorphism to B. Then we have this T phi M. That's actually an involutive subbundle, so it's a subalgebroid. So over there, when we just look at it in an abstract manner, we just can take a foliation, so an involutive subbundle of Tm. And then because you have an epimorphism, you know that gamma A mod J is locally spanned. You just see this by taking pullbacks of sections of B, and pullbacks of sections of B will generate A mod J over M. So it's locally spanned by sections A, or A is section of A, such that now how should I call it? That there exists a B, section of B, with A phi related to B, meaning that phi composed with A is B composed with phi. Right, so because we have an epimorphism of vector bundles, we can find those generators, those local sections for A or for A mod J, generating everything. I mean, those classes will generate A mod J, but if you take just those sections giving, well, that project n sections of J, you will have local frames for the whole of J, right? So the fibration is easy to understand in a sense. Okay, but here, this is expressed in terms of phi. You can actually reformulate this by saying that we have a flat F connection on A mod J given by these flat sections. So if you look at those sections, because of this locally spanned thing, you can actually say, okay, these sections are the flat sections of a representation of F on A mod J. Right? That's the idea. Again, if you want details, ask me later. But with this reformulations, you just get rid of phi, right? You just have now a vector subbundle J of A, an involutive subbundle F of Tm, and a flat, well, and a representation of F on A mod J that encodes the geometry of the fibration, right? And that's really the triple that gives you an ideal in a vector bundle first. Let's get to the definition. We're going to say that an ideal, first of all, in a vector bundle is a triple J, F, nabla. I didn't write nabla, but nabla, it's the connection. Such that, well, J is a vector subbundle, F is an involutive subbundle, and nabla is a flat F connection on A mod J. And now, if you assume that in addition, you had Lie algebroid structures on A and B, and phi was a fibration of Lie algebroids, then you're going to have the fact that, first of all, the diagram there is going to commute with the anchor. So you will have, first of all, T phi composed with the row of A is the row of B composed with big phi. That translates right away over here to the anchor of J being contained in F, right? Because if J is the kernel of this, so this side vanishes, and so the anchor of sections of the kernel have to vanish on the T phi, so it has to be in the kernel T phi M. So over there it has to be in F. And then also if A is phi related to B, then you have to have that row A of A has to be T phi related to row B of B. That translates to A nabla flat, implying that row A is nabla bot flat, nabla bot for the bot connection defined by F. And then you have that if A1 projects to B1, A2 projects to B2, that's really the Lie algebroid morphism condition for epimorphisms that works. You have that the bracket of A1, A2 has to be phi related to B1, B2. So sections that descend to B have to bracket to sections that descend to B, meaning over there, if A1, A2 are nabla flat, then the bracket of A1, A2 also has to be, right? And that's how you get this long definition. So an ideal in a Lie algebroid consists of three objects: an involutive subbundle F of Tm, a subalgebroid J of A, I'm ahead of it. Actually, it's just a subbundle for now. A subbundle J of A, which is anchored along F, and a flat F connection on A mod J, such that number two flat sections project to bracket two flat sections, compatibility with the anchor, flat sections project to, have as anchor nabla F flat sections. And the first condition I didn't even write down yet. If you apply this to A projecting to some B, and now a section J of J projecting to 0, that will imply right away that AJ has to project to be 0, so to 0, and that means that over here, a flat section and a section of J have to give that A with J is a section of J. And that's really the ideal condition. And I'm going to explain why.
For example,
an ideal energy algebra. Let's get there later. The other canonical example is the foliation on a manifold. But let's get there later. Yes.
Back to the condition of on F that it should be an involutive subbundle, because I don't get if it's not already included in the connection condition.
No, I mean, here I have the geometry situation given by the vibration, and here I extract what it is.
Yeah.
So if you have phi surjective subversion, then it's the tangent where the fibers define the foliation.
Yeah.
On M, so the tangent to the fibers is an involutive subbundle.
Yeah. Okay.
Right, and then I get rid of the vibration and I say, well, what I want to consider is an involutive subbundle of Tn. Right, because I want to reproduce this, but just starting from A and some data in A.
Yes.
And then the data in A is, well, you don't know little phi, but you're just going to take an involutive subbundle and you want N to be the leaf space of this involutive subbundle. Right? That's why I started with connected fibers here. Right, so I'm going to give you prototypes, but before I just want to explain, in fact, yeah, I'm just going to say it quick. So, in fact, that's the original definition that Cristian, Ortiz, and I came up with in 2010 or 11 when we were looking at actually the infinitesimal version of multiplicative foliations on Lie groupoids. So we came up with that, and we noticed that Hawkins had already some very similar structure the same structure in his paper on the quantization groupoid. I don't remember the title, some quantization paper on groupoids with polarizations. But actually, if you really look at it and you remember the naive ideals, so remember, asking for all sections of I, bracketing all sections of A into I was too much because you had the anchor to vanish. So now we replace this by saying, okay, I'm going to take a subbundle of A, but I'm not going to ask for all sections of A to bracket this subbundle into itself. But I'm going to say that I will do it only for special sections of A, right? That's what the connection says. So I have this subbundle, which becomes automatically a subalgebroid, and you have a connection, and you say that only the flat sections of this connection will bracket J into J. So if you look at the first condition, and that to answer your question, for instance, if F was 0 and nabla was 0, so you would just have J in A, then all sections of A would be flat because nabla was 0. And then that would just be the naive ideal condition, right? And the other two would be redundant because nabla is 0.
I mean, tangent bundle, isn't it exactly vector fields which respect the foliation?
Yes.
Yeah, so this is generalization of the algebra of vector fields respecting foliation. Yeah?
That's what happens over here, right? So the one is an ideal, it's really the ideal condition, and it took me several years actually to realize, but actually 3 is redundant, so we can get rid of it. I leave it as an exercise. So this anchor condition is redundant, and the ideal condition you can replace by the one I wrote down here to understand really better what happens. So assume, well, and also, let's not dwell on it, but J is automatically a subalgebroid. That's easy to show. J is a subbundle, but it becomes automatically a subalgebroid. And the ideal condition you can replace by the following. So you have your subalgebroid given by the structure. You can start with J being a subalgebroid, and you want to ask yourself, is this subalgebroid something I can quotient out of the Lie algebroid to get a reduced Lie algebroid? Well, in general, not. But the ideal condition is really equivalent to saying, okay, I have my bot connection defined by J, like over here. That's always given. That's a representation of J on A mod J, but it's very abstract. It's not anchored along the manifold. And finding a flat connection and a foliation on M such that Fj nabla is an infinitesimal ideal system, or ideal for short in A, is the same as saying that the connection, the F connection that you find on A mod J is really anchoring the bot connection along the manifold, right? Because the ideal condition is equivalent to the fact that, well, the ideal connection is geometrizing the bot connection. So nabla Jj of a class of A is nabla along rho of J of A. So you really make your wants to be reduction data, which is too algebraic, which just doesn't know enough. You anchor it along the manifold, and then you get your ideal structure. And in fact, in all my examples, or almost all the examples, you actually find F such that rho J equals to F, and then this condition is actually also redundant in that case. So if you have an infinitesimal ideal system, so if you start with your J sub-algebroid, and you find that the anchor of J is regular, so it's an involutive subbundle of Tm, and you find a flat connection on A mod J that does this, then you have an infinitesimal ideal system. And as I said, it's the same as finding, in that case, just finding flat F connection, so along the anchor of J, that is really making the abstract algebraic bot representation of J algebraic, geometric. Right.
Purely algebraic terms, maybe it's possible to replace your connection with just passing to the normalizer.
Of what? So, if you want
normalizer of J, yeah. So
then, yes, but that's a good question. But then you still need to make it geometric.
yeah, of course. Yeah.
Right, so another way to say it, actually this data, I'm almost done, is the same as actually foliation on A. So it's the same as the foliation on A. If you take the tangent bundle of A, then it's actually a doubly algebroid, and as in my number 3 description of ideals in the algebras, this triple, where the Fj nabla is equivalent to a foliation on A, well, so an involutive subbundle of Ta that is also sub-algebroid over Tm. That may be something
Yeah,
that...
of course, you're right. It must have geometrical taste, so to say.
Yeah. Geometric. So the triple is the same as a foliation on A that is compatible with the algebroid structure. So that's for the next slide. As I said, an infinitesimal ideal in a Lie algebra is just an usual ideal because you just have this ideal condition remaining. Same if F is 0, nabla is 0, you just have a naive ideal. And the third prototype really is an involutive subbundle where you take F as a sub-algebroid and as the involutive subbundle of the base and then the bot connection. So that would be reduction data for tangent bundles. So we now have ideas in tangent bundles, but actually there are more general ones that are more interesting where you play a bit with those two bundles. Right, and the very last slide is the following. Conversely, when you have this data, sorry, I always write ideal, but infinitesimal ideal system, right? But it's the right notion of ideal. So if you have an ideal in a Lie algebroid, and if the geometry is okay, so if the space of leaves of F in M is a smooth manifold and the connection has no holonomy, then you do have a Lie algebroid structure on this quotient. So A mod J mod parallel transport, which is the same as the space of leaves of this equivalent foliation, such that you have an epimorphism or a fibration of Lie algebroids. Right, and then I knew that I would be right on time here, and that I would not have time to talk about the ATIA class, but you never know. So we'll talk Thursday about obstructions to those structures. And here, so the paper with Rosa about the first part is on archive since last year, and the rest was in this foliated groupoids and infinitesimal ideal systems with Cristian Ortiz, which is only 11 years old.